Okay, so we're very glad to have Dr. Ki-Weon Seo, who is a professor in the Department of Earth Science Education at Seoul National University, and his research mainly focuses on examining ice mass loss from both ice sheets and sea level rise using satellite gravimetry and altimetry data, and currently covers regional sea level variation determined by gravitational change over West Antarctica. Uh, Dr. Seo is a co-principal investigator in the Lioness TG project, which is focused on ice mass loss in Thwaites Glacier, one of the leading causes for changes in gravity in the region. And prior to his current position, Dr. Seo was a senior research scientist at the Korea Polar Research Institute and a NASA postdoctoral fellow at the Jet Propulsion Laboratory. Dr. Seo earned his PhD from the University of Texas at Austin and his master's and bachelor's degree in science education from Seoul National University. Today, he will be speaking on the topic Understanding Sea Level Rise Using Satellite Gravity, 2003 to 2022, and Polar Motion, 1992 to 2016. So welcome, Professor. Thank you.
Okay, good morning, and thank you for inviting me to this NASA GIS Sea Level Rise seminar. So I'm preparing a topic of understanding sea level rise using these two different time periods. I have to separate study period into these two because during the first time period, we have satellite gravity data like GRACE and GRACE follow-on. But most of during the second period, since 1992, we don't have GRACE data. So we have to use another kinds of global measure of mass change. So I found that polar motion is really useful. So for this purpose, I'm going to use polar motion data for to study about sea level change during this second period. Okay, let's start with the first topic, understanding sea level rise using satellite gravity during 2003 to 2022. I think many people in this seminar already knew that about GRACE and GRACE follow-on. And these two satellite gravity data are very unique tool to measure time-varying gravity associated with surface mass change, including ocean mass change. But in this slide, I want to emphasize the limitation of GRACE data. Nominal resolution of GRACE data is about 400 kilometer. Due to this low spatial resolution, we have actually some problem when you try to look at mass change on Earth's surface, particularly over ocean. So what GRACE measure here is shown in MT is the combination of ocean mass change and land mass change. So when you try to look at ocean mass change from GRACE data, we actually have both ocean mass change and land mass change over ocean. This is because due to the low spatial resolution of GRACE data, land mass change is spreading out to ocean region. We call this leakage effect. So to understand ocean mass change, we have to be very careful to correct this leakage effect over ocean from land. So previously, a very simple and straightforward method was used. This figure comes from geodetic paper by Chambers in 2006. He used 500 kilometer buffer zone, shown here black color. So he calculated ocean mass change from GRACE data by excluding ocean region in buffer zone. So this method is quite straightforward and effective to suppress leakage effect. but at the same time, we are losing some important ocean signal along coastal region. So to resolve such a limitation in buffer zone method, Chen developed further modeling method. So if you are interested in technical detail about the further modeling, you may see these papers. But if I explain the benefit of a further modeling in this slide very briefly. So this is the GRACE observation. This is actually annual rate of mass change from land and ocean. So we have mass change from land and mass change from ocean. You can see very large negative anomaly in Greenland and West Antarctica. And the two regions are main source of sea level rise. But you can also see similar negative trend here over ocean. This is not actually signal from ocean. This is leakage effect from Greenland to ocean and West Antarctica to ocean. So for the modeling, actually iteratively adjust land mass change to obtain higher resolution leakage corrected mass change over land. So I denote this field using capital M because this is kind of higher resolution mass change. So you can see very sharp signal boundary between land and ocean. And by using this field, we can make this field smoothed like this way to make similar spatial resolution to GRACE observation. So we have small ml, kind of smoothed version of this higher resolution leakage corrected mass change, land mass change from further modeling. So we have land mass change and ocean mass change, and we have land mass change only. So by subtracting these two fields, we have leakage corrected ocean mass change. So this is actually, by using this way, we can suppress leakage effect. So this is the result of leakage corrected ocean mass change from a paper of John et al. In 2018. So in this presentation, I will call this field as observation of ocean mass from GRACE. So I use the small m OBS. But at the same time, we can also estimate ocean mass change from leakage corrected land mass change from further modeling. So if you look at left panel first, this is a case where extra ice mass is located like in Greenland and Antarctica. So due to this extra ice mass, we have a larger gravitational attraction force. So seawater move toward to this ice region. So sea surface deform like this way. And after this ice melting, like we have experienced it in Greenland and West Antarctica for last several decades, then global mean sea level should rise. But over ocean close to ice region, due to the loss of ice, gravitational attraction force decrease. So sea level should drop here. So this kind of unique sea level rise and drop pattern is called sea level fingerprint. We can use sea level fingerprint theory, and we can estimate ocean mass change by using sea level fingerprint theory and leakage corrected land mass signal from further modeling. So this is estimation of ocean mass change based on leakage corrected land mass change from further modeling plus sea level fingerprint theory. So we call this estimation in this presentation. And also I want to emphasize this field is actually kind of higher resolution because in this theoretical estimation, any smoothing effect was not involved. So this is smoothed observation, and this is the estimation with higher resolution. Then I'm going to compare these two fields in later slide. Okay, the first result is that this is the global ocean mass variation based on higher resolution estimation during this time period. This is for during grace time period. This is for grace follow-on period. We have less than 1 year gap between grace and grace follow-on. I removed a seasonal component, and the sea level rise rate is about 2.00 millimeter per year. And this estimation actually can be compared with observation. Because observation already smoothed, I need to apply some smoothing operator to this field to make smoothed estimation. Then we have black line shown here about estimation, and red line is observation. So both observation and estimation show almost identical variation. This is not actually a surprising result because GRACE data should provide ocean mass change, which has the same amount of land mass change with opposite sign. Because estimation is based on land mass change, these two numbers should be the same. But more interesting comparison can be found in 6 different ocean basins. So I selected North and South Pacific Oceans, Indian Ocean, North and Atlantic, South Atlantic Oceans, and Arctic Oceans. So black line is smoothed estimation, and red line shows smoothed observation. And for your comparison, I also included a number in the case of applying without applying any smoothing for the estimation. So you have a slightly larger number, like here. So if we have perfect ocean mass observation from GRACE, and also if we have perfect observation of a land from GRACE, and our theory for sea level fingerprint is perfect, then estimation and observation should be identical. We call this self-consistency of GRACE data. So basically, you can see quite great self-consistency between observation and estimation in 6 different ocean basins. But problem is that in North and South Atlantic Ocean, our estimation and observation show some non-negligible trend differences. Unfortunately, we don't have any answer to explain these differences. So this is quite important question to answer for future. And I think the most important feature in this slide is in Arctic Ocean. Both estimation and observation show negative sea level trend. I think this is quite natural because Arctic Ocean is surrounded by land mass where huge ice is melting. So due to the loss of ice and resulting gravitational attraction force decrease, mass sea level change over Arctic Ocean should be also decreased. Okay, so based on this self-consistency, we can say that our estimation without applying any smoothing would be closer to true variation of ocean mass. So from now on, I'll compare our estimation to another kinds of independent sea level change observation, this kind of validation process. So I'm going to compare with satellite altimetry data. We have total sea level change observation from satellite altimetry data. So I used ensemble mean of these 3 different data center. So altimetry observation is kind of total sea level change observation. And this can be also explained by these 4 different sea level change contributors. So I used steric effect from ensemble mean of these 3 different data center. and mass effect that I just showed you in previous slide from GRACE and GRACE follow-on data. And I additionally include ocean dynamic effect and seafloor deformation. So some of these is kinds of total sea level change estimations. Then I will compare observation and estimation of a total sea level change in later slide. So this is a comparison between observation and estimation because we don't have good altimetry data and steric data in Arctic Ocean. I didn't include Arctic Ocean region. So this is the North Pacific Ocean, South Pacific Oceans, North and South Atlantic Oceans, and Indian Ocean. And this is for global ocean. So gray line shows altimetry observation for total sea level change. This is the observation. Black line shows estimation of total sea level change by summing these 4 different sea level change contributors: steric effect, mass effect, ocean dynamic effect, and seafloor deformation. For global ocean, we have very nice agreement between observation and estimation. For 5 ocean basin, we also have very close agreement between observation and estimation. And this is a summary of sea level rise rate for global ocean and 5 different ocean basins. So if we look at global ocean first, gray bar chart shows annual sea level rise rate from satellite altimetry observation, and black bar shows the total sea level change rate by summing these 4 different contributors. We have very close agreement, and more importantly, this number is mostly explained by mass effect. Other ocean basin, in other ocean basins, we also see similar comparison agreement, except again, North Atlantic Ocean. We have some non-negligible discrepancies between observation and estimation. So again, we don't have any good answer for this. Okay, now let's look at local region, particularly coastal region. So I selected 6 different coastal area: Arabian Sea, southern Alaska, west coast of the United States, southern Greenland, Western Europe, and Chile coast. So again, gray line is satellite altimetry observation, black line is the sum of these 4 different contributors. Well, generally, altimetry observation and estimation show very close variation. So in this case, compared to global ocean and 5 different ocean basins, actually steric effect is much more important than the mass effect. Okay, this is the sea level rise rate summary. So if you look at this first, this is observation and this estimation from 4 different sea level rise contributors. Well, there is some large discrepancies in Western Europe and also in Arabian Sea, but I think it's quite natural because we are talking about quite smaller region, particularly close to coastal area. So we have lots of uncertainty in static data and altimetry data, even in GRACE data, because we try to correct leakage effect from GRACE data, but the correction should not be perfect. And in this slide, I think the most important and interesting feature is found in southern Greenland. Satellite altimetry data shows negative sea level trend, and this is actually explained by mass effect, negative mass effect, and static effect, plus large crustal uplift. This is actually due to huge ice mass melting in southern Greenland. So to compensate this ice mass loss, crustal should be uplifted. So we have quite complicated geophysical processes in southern Greenland, and our analysis explain this very well. Okay, now let's look at, let's expand our data up to grace follow-on period. So again, this is a global ocean and 5 different ocean basins. But unfortunately, we have quite large difference between observation and estimation during grace follow-on period for global ocean, North Atlantic Ocean, South Atlantic Ocean, and other basins too. So, but fortunately, in early this year, this paper actually provided refined altimetry data and steric data. So by using this refined data, we can compare estimation and observation again. Because those data sets provide until December 2022, we expanded analysis until this time. So now for global ocean, we have very nice agreement during grace follow-on period again. And we have quite good agreement other basin, but still we have some issue in North Atlantic Ocean. And for coastal region, we have good agreement during grace follow-on period in some region, but still we have some issues like Arabian Sea and Western Europe. So I think during grace follow-on period, after 2019, we have much room to improve in satellite altimeter data, static data, and maybe grace follow-on data. So this is kind of issue for sea level change study. Okay, this discussion, I haven't talked about glacial isostatic adjustment, GIA, in the previous slide. GIA is kind of mental mass redistribution. So actually, grace observe any kind of mass change from mantle and, for example, water on a surface. So to obtain water mass redistribution from grace data, we have to remove mantle effect. So people actually using GIM model to correct GI effect. So in my slide previously, I used Peltier GI model for the processing of grace data. But there are other kinds of GI model, like one of a kind is Ki-Weon model from JPL. So if we use Ki-Weon GI model instead of Peltier GI model, we have quite different number of ocean mass change. So this is comparison between different the case of GI model. So black line is the same plot that I showed before when I used Peltier GI model for the processing of grace data. But if we include Ki-Weon GI model instead of a Peltier GI model, we have quite different number. So this number, 2.4 millimeter per year, is approximately same to the entire ice mass melting from Antarctica and its contribution to sea level change. So this is not actually a small number, it's a huge number. And also 6 different ocean basins. Black line is a case of using Peltier GI model, and blue line shows when we use Ki-Weon GI model. So you can see quite large trend difference in 6 different ocean basins except Arctic Ocean. We have quite good similar variation in Arctic Ocean regardless of using GI model. So which GI model we use? We have quite different number of ocean mass change. Okay, this is conclusion number 1. I show you that grace and grace follow-on have successfully observed and estimated ocean mass change globally and regionally. I try to validate our estimation using grace and grace follow-on data with satellite altimetry and Argo float system. And this shows the validations are quite promising in global ocean and ocean basin scale. But we have some large discrepancies during grace follow-on period and also in some local region. due to some unknown uncertainty of different observational platform. Okay, let's move on to the second topic, understanding sea level rise using polar motion during 1992-2016. In this slide, I want to explain the motivation of this using polar motion. So in my presentation, the first part of my presentation, I show you GRACE data is useful to understand ocean mass change. So blue line is GRACE data, explain the global mean sea level change. And also red line is actually estimation of global mass change from 1992 to 2016 based on these 6 different data sets. I used Antarctic ice mass loss, Greenland ice mass loss, mountain glacier, soil moisture, snow, dam, and groundwater. And among these 6 different sea level rise contributors, it's quite surprising to see that groundwater depletion is kinds of very large sea level rise contributors during these past 3 decades, comparable to mountain glacier and Greenland. So if we remove the seasonal component of this time period, we have this clear trend and interannual variation. So again, during grace period, we have very close agreement between estimation and observation. Both shows very close sea level rise rate, 2.05 or 2.09 millimeter per year. But prior grace era, the estimation showed that sea level rise rate is about 1.13 millimeter per year. So the question is that how can you confirm this approximately 3-decade-long sea level rise estimation would be true? In addition to this, huge groundwater depletion and its sea level rise would be true. So for this, I need to use independent data set to confirm this variation. So obviously, the easiest way is to using satellite altimetry data. So this number is actually obtained from satellite altimetry data during the study period. So 6 different sea level rise contributors need to explain this number. But we have to start with GIA effect because GIA make ocean basin get larger. So sea level drop about 0.3 millimeter per year. So starting from the GIA effect, we have to add static effect first, and then need to add sea level rise contribution from Antarctic ice mass loss, Greenland, mountain glacier, soil moisture, dam, and groundwater. And the sum is located here. Actually, it's not good. This is probably because we don't have good static data during 1990. I used WOA 18 static data, but some static data prior 2005 shows quite large number. So due to the uncertainty in static data, we may not use altimetry data to explain these 6 different sea level rise contributors. So second choice would be using Earth's dynamic oblateness because this observation doesn't affect by static sea level change. So basically, if we have ice melting in high latitude, the melted water move to low latitude where most of the ocean is located. So in this process, the Earth's dynamic oblateness increase. So this Earth's oblated dynamics is actually another kind of measure of global mass change. So again, 6 different sea level rise contributors need to explain observed Earth's dynamic of lateness. And here, we also need to start from GIA. GIA effect also affect Earth's dynamic of lateness, and we used GIA model for this. But issue is that different GIA model showed quite different number of Earth's dynamic of lateness. So anyway, many people using a peltier GIA model. So I'm going to start with peltier GIA model, Earth's dynamic of lateness, and add its effect to Antarctic ice mass loss, Greenland, glacier, soil moisture, dam, groundwater, and also Earth's dynamic of lateness is affected by ocean bottom pressure and surface pressure. I also included these effects too. So the sum of these contributions located here. So I think it's quite good. Our estimation and observation very close to each other. But again, the problem is that which GI model we used, the resulting the result is quite different, like here. So depending on GI model, we have quite different number. And also groundwater effect to sea level change is very insensitive to Earth's dynamic of lateness. So using this observation, we cannot confirm groundwater effect is really important to sea level change during last 3 decades. So I have to finally use polar motion. Polar motion refers to movement of Earth's spin axis relative to geographic axis. So why do we have polar motion? Well, actually, for example, water and air mass moving around continuously on our surface, north and south, west and east. This relocation, redistribution of water and air mass change perturb the angular momentum. But entire Earth system should conserve angular momentum. So for this, the Earth spin axis should be relocated for the conservation of angular momentum. So that's why we have polar motion. So this is actually observation of polar motion since 1900. And this is X direction of polar motion. This is a Y direction of polar motion. So X direction is toward to Greenwich meridian, and Y direction is toward to 90-degree east longitude. You can see very clear oscillation in polar motion, shown here in thin black line. We call this Chandler wobble. This is kinds of free oscillation of Earth. So we have to remove this Chandler wobble component. And then residual are shown here, thick black line. We call this polar motion excitation. And the variation of polar motion excitation actually represent our spin axis relocation corresponding to angular momentum change of air and water mass. So we are going to use this polar motion excitation as the observation, and then we are going to compare estimation of polar motion excitation from sea level rise contributor and with an polar motion observation. Okay, I want to explain briefly how I estimate polar motion excitation. So this is a case of groundwater depletion. You can see I obtained this data from WADA model. You can see huge groundwater depletion in northern India, some part of China, and Middle East, and United States. And this is only for land mass change. But as I talked to you before, based on land mass change and sea level fingerprint theory, we can estimate ocean mass change. So we have land mass change and ocean mass change. So we have a global mass change. So this land mass change and ocean mass change, and we have a global mass change from the groundwater data. And these global mass change can be represented by spherical harmony coefficient, CLM and SLM. Among these, C21 and S21 are directly connected to polar motion excitation, Chi1, Chi2, X direction, and Y direction. So by using this process, we can estimate polar motion excitation from 6 different sea level rise contributors. Okay, so this is estimation of polar motion excitation. Red line is Chi1, I mean X direction, blue line Chi2, Y direction. So this is the polar motion excitation change from Antarctic ice mass loss, Greenland, mountain glacier, soil moisture, dam, and groundwater. Unit is milliarcsec. 1 milliarcsec is about 3 centimeters on Earth's surface. So we have 6 different kinds of polar motion excitation associated with sea level change. And because polar motion is also affected by barometric pressure, ocean bottom pressure, wind, and current. So I need to additionally consider 4 different polar motion excitation. So now we have 10 different kinds of polar motion excitation. And then I'm going to make some of these to compare with polar motion excitation observation. Okay, this is the comparison between observation and estimation. So if you look at left panel first, this is the Chi1, I mean X direction and Y direction of polar motion. And blue line shows observation. And red line is estimation. So red line is actually some of these 10 different kinds of contributors. And after we remove seasonal component, we have this variation. So I think it's not that bad. It's quite good actually. But we have some trend difference between observation and estimation in Chi1. So again, in this calculation, I actually used GIA model from Peltier for GIA polar motion. But again, the problem is that we have quite different kinds of GIA polar motion. So this arrow shows GIA polar motion from different GIA model and different polar motion observation. So depending on which GIA polar motion we use, we have quite different comparison. So this is a very good case to explain the importance of GIA polar motion. On your left, this is the same plot that I showed you before when I used Peltier GIA model. So the comparison between observation and estimation show like this. So we have some trend difference in Chi1, in Chi2. But when we use Purcell GIA polar motion, we have very different trend. So observation, estimation show quite different variation here. So if we use Purcell GIA model for GIA polar motion, our understanding for past sea level change from 6 different sea level rise contributor estimate to this would not be true. So the choice of GIA polar motion is really important for this purpose. And in 2021, my colleague and I actually published a paper in Journal of Geodesy to refine GIA model for GIA polar motion. So I don't want to talk about technical detail about the methodology. So if you are interested in, please this paper. So anyway, the methodology developed in this paper, we can refine GIA model to have better GIA polar motion. So this is the result. Again, this is the same plot I showed you before when I used Peltier GIA model for GIA polar motion. But if I refine, after I refine GI polar motion in GI model from Peltier, we have a better agreement, trend agreement between observation and estimation. Now we have quite close trend agreement between the two. This case more dramatic. For Pulsar case, we have quite large trend difference here. But after we refine GI polar motion, we have very nice agreement between polar motion observation and estimation. And I think this result is quite impressive because I'm talking about polar motion, and I'm talking about 10 different kinds of data and model. So those combinations show really great agreement between observation and estimation. What this means is that Earth science community are doing their job really well. So if we combine all different kinds of data set, explain Earth's angular momentum, we really well explain observation of polar motion. So based on this nice comparison, we can actually explain groundwater depletion effect. So this is the polar motion excitation rate from different sources. Red arrow show GIA. This is for Greenland ice mass loss, mountain glacier, Antarctic ice mass loss, and dam. And finally, groundwater. Groundwater effect is actually the largest contributor to polar motion excitation among these water mass change next to the GIA. And some of these estimation located here, and observation of polar motion also located here. So our observation and estimation are very close to each other. And if we don't include groundwater effect, our estimation actually located far from the observation. So this result actually indicate that groundwater depletion and its sea level rise contribution estimated from water model could be true. Okay, this is conclusion number 2. Estimated polar motion excitation agree really well with polar motion observation. And each sea level rise component from 6 different sources explain very well about past sea level change prior to GRACE observation based on this comparison. I think this part is the most important. We have a quite long polar motion data since late 19th century. So maybe if we use this long polar motion data, we may understand past climate change prior GRACE observation. Okay, I think I'm talking about pretty much what I prepared. Thank you very much.
Okay, thanks so much, Professor. Do we have any questions? Yes, Gavin has a question.
Hi, thanks for a very interesting talk. In the last part where you're comparing the different impacts, are there still residual physical processes that are not included? I'm thinking about things like increased reservoir building, for instance, that might change the terrestrial water store, or the change of floating ice that wouldn't be captured by GRACE, but would impact the mass distribution in the ocean.
Yes, there should be many different kinds of contributor to polar motion. So as you talked to, I think those can be explained by some residual. And I think the most important part should be kinds of actually convection of outer core.
Right.
People actually expect that those contributions should be very large, but we don't have any good model for this. So that may be another important contributor to polar motion. So yeah, so artificial reservoir effect already explained by the dam. So because I use dam. So I think that part is actually included in this analysis.
Okay. Okay. Yeah. No, I would have guessed that the very longest term trends in polar motion were related to kind of dynamo effects
Yes.
in the core, right? But what you're showing here is that at least in the last 30 years, those
Yes.
trends are due to changes in the surface mass distribution,
Yeah.
not in the core, right? Is that what I should take back?
Yeah. Yeah. So yeah. So I think the actual polar motion has I mean the angular momentum Earth's rotation vector has three different components. XY component is for polar motion. Z component is this the rate of spin, so it's kind of length of day.
Right.
So we already know that outer core convection heavily affect length of day change.
Oh.
So it's very difficult to understand length of change for the purpose of surface mass change understanding. But if you look at this comparison, probably outer core convection may be included in this residual, but it's not as significant as what expected. So anyway, we have to look at longer term variation. So for this, to confirm this.
Yeah. Okay. Well, thank you very much.
Thank you.
Any other questions? So I was kind of wondering about the longer term variations going back further in time. You can comment on like some of the challenges or what can be done there.
Yeah, but to do that, we need to have very good other kind of data.
I see.
So
Right.
polar motion is kind of collectively analysis of very different kind of data sets. So we need good data to for the past kind of historical mass change of the Earth.
Right. Right. Okay. Any other questions? Well, I guess we can stop there. There's no other questions. So thanks again, Dr. Seo, and thanks everyone for coming.
Okay, thank you very much.